Venus, our closest planetary neighbor, often called Earth's twin. Similar size, similar gravity. Sounds
Yeah.
almost cozy, right?
Almost, yeah. But that comparison only goes so far.
Except Venus is less twin, more evil twin.
Mhm.
It's a scorching high-pressure nightmare. The surface temperature averages around 464 degrees Celsius.
That's hot enough to melt lead. Easily.
Lead, tin, maybe your hopes for surface base. And the atmospheric pressure, a crushing 92 times what you feel here at sea level.
It's like being nearly a kilometer deep in Earth's ocean, just immense pressure.
All thanks to this runaway greenhouse effect, right?
Yeah.
Driven by an atmosphere that's, 96.5% carbon dioxide?
Pretty much entirely CO2. It traps heat incredibly effectively.
It's the ultimate planetary paradox. But what if? What if the secret to Venus isn't figuring out how to survive on that hellish surface, but how to completely avoid it?
Now that's an interesting way to frame it.
That's the absolutely fascinating idea we're diving into today. We've taken the stack of sources you shared, articles, research papers, some seriously ambitious concepts, and we're going to unpack them.
Sounds good. There's some really thought-provoking stuff in there.
Our mission: explore the science and engineering behind not just visiting Venus, but building cities in its skies.
Exploding cities, yeah.
And then we'll lift our gaze even higher to the truly mind-bending vision of potentially encircling the entire planet with artificial cloud continents.
That one's definitely ambitious.
Because, believe it or not, high above that deadly ground, there's a surprising niche, a seemingly Earth-like environment just waiting.
Okay, let's unpack this.
What's fascinating here, I think, is how these concepts force a radical shift in our thinking about planetary exploration.
Oh, so?
Well, instead of focusing on landing on the surface where conditions are the most extreme, you look for the spot where they are least hostile.
And according to the sources you provided, that spot is way up in the upper atmosphere.
Exactly. Specifically in a band between about 50 and 56 kilometers altitude, while the surface is, molten lead territory.
Right.
This layer is surprisingly temperate.
Temperate? How temperate are we talking? Like actually temperate? Well, within that range, you're looking at temperatures from 0 to 50 degrees C.
Okay.
And if you pinpoint around 56 kilometers, the sources show it settles in at a comfortable 20 degrees C.
20 degrees Celsius, like room temperature.
Pretty much, like a pleasant spring day here on Earth.
That's incredible, especially compared to 464 degrees below. And what about that crushing pressure you mentioned? Is it also extreme up there?
No, that's another huge advantage of this altitude. The pressure is remarkably close to Earth's sea level pressure.
Really?
Yeah. At 50 kilometers, it's about 1 bar, basically what we feel right now. And even at 56 kilometers, it's only dropped to around 0.56 bar.
Half an atmosphere.
Which means any habitat at this height wouldn't need heavy, rigid pressure vessels like you would on the Moon or Mars. The pressure difference between inside and outside would be minimal.
Minimal pressure difference.
Yeah.
Okay, that's a game changer for building anything, isn't it?
Absolutely. Structurally, it simplifies things immensely.
But the really compelling part for long-term human presence, based on the sources, is the gravity at this altitude.
Yes, that's a huge factor. At 56 kilometers up, the gravity is approximately 90% of Earth's surface gravity.
90%.
Compare that to Mars at 38% or the Moon at just 16%.
Wow.
For human health over months or years, that near-Earth gravity is a massive benefit. It could potentially avoid or significantly mitigate the bone and muscle density loss we worry about in microgravity or lower gravity environments.
Plus, you've got this incredibly thick atmosphere above you acting as a natural radiation shield.
Right. It's equivalent to about 1 kilogram per square centimeter of shielding. That's far more protection from solar and cosmic radiation than you'd get without, extensive heavy shielding on the surface of Mars or the Moon.
Makes sense. And thinking about resources, you've got abundant solar energy up there, right? Well above the main cloud decks.
About 1.9 times the intensity we get in Earth orbit, so plenty of power potential.
And the sources point out you might even capture light reflected upwards from Venus's incredibly bright cloud tops below.
That's another potential energy source, yeah.
Yeah.
And crucially, many of the elements needed for life support and local manufacturing, what's called in situ resource utilization, or ISRU.
Using what's there.
Exactly. They're present in the atmosphere itself. Carbon and oxygen in the CO2, obviously. Nitrogen for the buffer gas and breathable air, and hydrogen and sulfur. Well, they're tied up in the sulfuric acid clouds.
Ah, right, the clouds.
Yeah. But the basic ingredients are there.
So when you look at the comparison charts in your sources, like Table 1, which lays out the surface conditions, versus this 56 kilometer band versus Earth, It becomes clear why this altitude is described as potentially the most Earth-like environment, other than Earth itself, in the solar system.
It really is a stark contrast. Temperature, pressure, gravity, radiation shielding. It ticks a lot of boxes.
It's a stunning contrast to the lethal surface below.
It is, but you mentioned those sulfuric acid clouds. That sweet spot for temperature and pressure is smack in the middle of them.
Ah, the catch. So while the pressure and temp might be good, you're essentially floating inside a cloud of concentrated battery acid.
Pretty much. And that corrosive environment is the immediate major engineering challenge for anything operating at that altitude. It demands incredibly resistant materials.
Which brings us to the core idea. Floating habitats, essentially massive balloons or airships, what the sources call aerostats.
Aerostats, right.
That leverage Venus's dense CO2 atmosphere for buoyancy. This isn't just science fiction, is it? It's a concept that's been seriously studied.
Oh, yeah, for decades. Notably championed by scientists like Jeffrey Landis at NASA. He envisioned large, permanent settlements.
And he had this key insight, right?
Yeah.
About using breathable air itself as the lifting gas.
Exactly. Because Venus's CO2 atmosphere is so much denser than our air, regular air, a standard oxygen-nitrogen mix like Earth's atmosphere, is actually buoyant in it.
It seems so counterintuitive. You fill a big balloon with regular Earth air and it just floats in the Venusian atmosphere.
It does. It's like filling a balloon here on Earth with helium, but instead of helium, it's just air, and instead of our air, it's Venus's thick CO2.
Wow.
And the scale of lift is incredible. Landis calculated a 1-kilometer diameter sphere filled with breathable air could lift something like 700,000 tons.
700,000 tons.
Yeah.
That's heavier than 2 Empire State Buildings combined.
It's immense lift capability. And the elegance of using breathable air is that the lifting gas is the habitat atmosphere. Your entire volume inside the sphere is livable space. No separate gas bags needed inside.
Okay, that's clever. And NASA's AVOC program, the conceptual study, also explored this, didn't it? Using airships for exploration.
Yeah, AGOC looked at phased crewed missions using airships specifically for atmospheric exploration. It mapped out a potential path and start with robotic scouts, then short crewed missions and airships, maybe scaling up to potentially permanent human presence eventually.
The stepping stone approach.
And concepts like these have roots in even earlier ideas, like Sergei Zhytomyrsky's floating islands from the 70s, I think. The basic principle of atmospheric buoyancy on Venus has been kicked around for a while.
Looking at the design details from the sources, buoyancy is obviously fundamental. You mentioned breathable air giving lift. About 0.28 kilograms per cubic meter at 56 kilometers.
That, yes.
But hydrogen offers significantly more lift per volume, right? Nearly 3 times as much.
Yeah, hydrogen gives you around 0.78 kilograms per cubic meter at the same altitude. Much more efficient lift.
So why not just use hydrogen then? Seems like a no-brainer for lift.
Well, it comes down to ISRU and leakage. Hydrogen isn't just sitting there. You'd have to constantly produce it from Venusian resources, likely from the sulfuric acid, to replace what inevitably leaks out. And hydrogen molecules are tiny. They tend to leak through materials more easily than larger nitrogen and oxygen molecules in air. However, a major plus for hydrogen on Venus is that the atmosphere has almost no free oxygen. So the fire risk from hydrogen leaks, which is a big concern here on Earth.
Like the Hindenburg.
Exactly. That risk is very, very low up there. But using breathable air avoids the need for that continuous hydrogen production just for lift, although you need much larger structures for the same payload. Trade-offs.
Got it. Trade-offs. And you mentioned the structural advantage of near-Earth pressure earlier. That's huge, too.
Yes, absolutely huge. Because the pressure inside the habitat is so close to the pressure outside, you don't need heavy reinforced metal hulls like you would on the Moon or Mars to contain, say, 1 atmosphere of pressure against a vacuum.
So what do you use?
You can potentially use lightweight, flexible materials like reinforced fabrics for the envelope. Think high-tech dirigible materials, but scaled up and acid resistant.
And if it tears, no explosive decompression.
Exactly. A puncture wouldn't cause a catastrophic failure. It would be a slow leak, maybe over thousands of hours, depending on the size, giving plenty of time for detection and repairs. Much safer in that respect.
That's a fundamental design advantage. But as you said earlier, sustainability relies entirely on ISRU, using what's already there.
Absolutely critical. You have to live off the land, or in this case, off the air.
Oxygen and carbon are readily available in the CO2 atmosphere. That seems straightforward enough. Nitrogen is there for the breathable air mix, buffer gas.
Check, check.
The real challenge, as the sources highlight, is getting water and hydrogen.
That's the crux of it, yes. Because you need water for life support and hydrogen for potentially making fuel or for extra lift if you go that route.
And that's where the sulfuric acid clouds come back in, H2SO4.
Right. The plan generally is to collect the minuscule sulfuric acid droplets suspended in the atmosphere and process the H2SO4 to extract hydrogen and oxygen.
How do you do that?
Typically involves decomposing the acid, often thermally, and then using electrolysis to split the resulting water or sulfur dioxide and oxygen. There are different chemical pathways proposed.
But studies like the VIP and SPR concept point out the difficulties, don't they?
They do. Those H2SO4 droplets are very dilute, like a haze or fog, not a dense cloud like we might imagine. So you have to scoop up and process truly vast volumes of atmosphere to get a useful amount of acid.
Okay, volume is one issue.
And the chemical processing itself is complex. Sulfur compounds are notorious for poisoning the catalyst needed for efficient electrolysis. That means lower efficiency, needing more energy, and potentially needing to replace catalysts frequently. It adds significant technical hurdles and energy costs to what sounds simple on paper, just grab the acid.
Right, it's never quite that simple. Which leads directly to the other big engineering challenges for even these, let's call them simpler floating cities.
Exactly, it's not just about floating.
Okay, so beyond resource processing, what else stands in the way? Materials, I imagine, because of that acid cloud you keep mentioning.
Precisely. The need for advanced materials is paramount. Anything exposed to the outside the airship envelope, sensors, equipment, robotic arms, solar panels, maybe has to be highly resistant to concentrated sulfuric acid.
And not just the acid, right?
No, it also has to tolerate intense UV radiation above the clouds and the thermal cycles as the habitat potentially moves through different altitudes or day-night cycles.
Are there materials that can actually do that for long periods?
Candidates like fluoropolymers, think materials related to Teflon, PTFE, are often mentioned because they have excellent chemical resistance. Composites incorporating these might work, but testing their long-term durability, and we're talking decades, even centuries, for permanent habitats under those specific Venusian conditions, the combination of acid, UV, temperature, that's essential research that still needs a lot of work. Degradation over time is a major concern. How long does even the best material really last?
And building these things, you can't exactly lay a foundation, can you? You're building them in midair.
Essentially, yes. Construction, expansion, and maintenance of potentially enormous structures floating kilometers above the surface without any ground support. It's an immense logistical challenge.
How have you even approached that?
You'd be heavily reliant on autonomous robotic systems for almost everything. Assembling sections, making repairs, installing equipment.
And the robots need to be acid-proof, too.
Exactly. Those robots also need to be acid-resistant, highly dexterous, and capable of complex manipulations in a dynamic atmospheric environment with winds and potentially turbulence. It's a huge robotics challenge.
Okay, acid-resistant robots, building acid-resistant fabric cities floating in acid clouds. That paints quite a picture. But even if you solve all that, there's a more fundamental limitation mentioned in the sources, right? Something missing from the atmosphere itself.
Yes, a major bottleneck that limits the scale and complexity of what you can build using only atmospheric resources. The atmosphere, while rich in carbon, oxygen, nitrogen, and sulfur,
Lacks metals.
lacks essential metals. Iron, copper, aluminum, silicon, titanium. Things you need for advanced manufacturing, electronics, motors, wiring, complex machinery, even basic stuff like screws or structural frames beyond the envelope itself.
So you could build the basic habitat structure, the envelope, and generate air and maybe water. But for anything requiring complex components or heavy industry.
You're stuck importing pretty much all of that from Earth, at least initially.
Or from the Venusian surface.
Or from the Venusian surface, if you could develop a reliable, large-scale way to mine materials in that hellish environment and then transport potentially millions of tons of material kilometers upwards into the atmosphere, that's another monumental challenge in itself.
Right, so without that surface to air supply chain, your capability for complex manufacturing and significant growth within the atmosphere is severely constrained. You're dependent on imports.
Exactly. It really puts a potential ceiling on how large or technologically self-sufficient those isolated cloud cities could become, at least using only atmospheric ISRU.
Okay, so that's the vision for floating cities, incredibly ambitious, facing serious material and resource challenges, but maybe within reach in the coming century with focused development.
Plausibly, yes. It's a stepwise approach.
But what about the really grand vision, taking this sky concept and scaling it up, scaling it way, way up to transform the entire planet.
Ah, full Venusian terraforming. Now we're talking about an undertaking of truly astronomical scale.
Yeah. As you mentioned earlier, the checklist is daunting. You'd need to drastically lower the surface temperature from over 400 degrees C down to something habitable.
Manage that immense atmosphere, 90 bars of mostly CO2, that's the big one.
Create a breathable nitrogen-oxygen mix.
Yeah.
Somehow import vast quantities of water. Maybe even figure out how to speed up its incredibly slow rotation.
Yeah.
Though that's usually seen as a secondary issue.
And based on the sources, the single biggest hurdle across all terraforming proposals, no matter the approach,
Is the sheer mass of that CO2 atmosphere.
precisely. We're talking about roughly 4.63 times 10 to the 20th kilograms of carbon dioxide. 463,000 trillion metric tons.
That number is hard to even comprehend.
Doing anything significant with that, removing it, sequestering it, converting it, requires energy and material processing on a scale that is almost unimaginable by today's standards.
Which brings us to this fascinating concept from Alex R. Howe, his cloud continents proposal from 2022. This concept takes the floating idea to the absolute extreme, doesn't it?
Yes, it's a vision for full terraforming, but instead of fixing the surface directly, it proposes essentially encircling the entire planet in an artificial global atmospheric shell that is itself habitable.
Encircling the entire planet, a shell. How would that even work? What holds it up?
The core idea is to build a continuous, load-bearing surface, the continent, that floats at that familiar 50-kilometer altitude, stretching all the way around the globe.
Good.
This shell would create a physical barrier, separating the super-dense, hot CO2 atmosphere below from a new, engineered, breathable atmosphere above it.
And what holds this global shell up? You can't just float a roof over a planet, can you?
It's not just a roof. It would be supported by an incredibly extensive, multi-kilometer tall, honeycomb-like lattice structure beneath the surface. Think of a vast planetary-scale structural grid.
A floating honeycomb.
This lattice would be filled with lifting gases the sources suggest primarily atmospheric nitrogen, which is abundant, supplemented perhaps by oxygen generated from the CO2. The design involves carefully managing pressure differentials layer by layer within this deep lattice structure to keep the whole massive shell afloat under its own weight, plus the weight of the new atmosphere and everything built on top.
Okay, a floating global honeycomb structure kilometers deep.
Yeah.
How in the world do you build something like that planet-wide? Where do the materials come from?
This is where the concept gets even more audacious and utterly dependent on advanced ISRU. The plan relies heavily on using in-situ resources, but not just collecting atmospheric gases or trace acid. The primary structural material for this global shell and its support lattice is envisioned as carbon nanotubes, or similar, incredibly strong, lightweight nanostructures.
Carbon nanotubes. Okay, strong and light. But where do you get tons? No, millions of tons. No, billions, maybe trillions of tons of carbon nanotubes. You can't ship those from Earth.
You make them there, directly from the atmospheric CO2.
Wait, what?
The concept proposes using immense amounts of solar power collected above the shell to break down the CO2 gas into its constituent elements, carbon and oxygen. The carbon is then used to synthesize the carbon nanotubes needed for the structure itself. The oxygen can be used either as a supplementary lifting gas in the lattice or vented to help form the breathable atmosphere above the shell.
So you're literally turning the primary problem, that massive CO2 atmosphere, into the building material for the solution.
Exactly. The CO2 isn't removed in the traditional sense. It's fundamentally transformed and repurposed into the very structure of the new world. The carbon becomes the backbone of the cloud continent.
That's conceptually elegant in a terrifyingly huge way. What about other materials? Metals? Silicon?
Those would still be needed. Metals and other elements not readily available in the atmosphere would still need to be mined from the Venusian surface and transported up to the construction altitude. So that surface mining and transport challenge remains.
And what about the atmosphere above this shell? What goes on top?
That upper layer would be engineered to become a breathable atmosphere, likely a nitrogen and oxygen mix, similar to Earth's, probably aiming for around 1 Earth atmosphere of pressure at the shell's surface.
And water. You still need water for a biosphere.
Right. You'd then need to import what the source calls comparatively modest quantities of water. Now, modest here is relative to the truly colossal amounts needed for some other terraforming plans that aim to create deep oceans on the surface.
Okay.
But you'd still need to bring in a significant amount of water, probably from asteroids or comets, to kickstart a potential hydrosphere, maybe shallow lakes or rivers, and a biosphere on the shell's surface.
So what's the timeline on this cloud continent? Building a planet-sized shell out of atmospheric carbon. Next century. The one after.
The projection from the source paper is a minimum of 200 years,
Ah.
and that's explicitly described as an extreme best-case scenario.
2 centuries, best case.
And it hinges entirely on massive, almost unimaginable technological leaps, particularly in achieving planetary-scale carbon nanotube manufacturing directly from atmospheric CO2 using solar energy. The required efficiency and sheer throughput are unprecedented.
And the challenges. Beyond just making the nanotubes, building a global shell seems prone to issues.
Unprecedented is definitely the word. The challenges are mind-boggling. First, there's the scalability of that CNT production. Can we really develop reactors that can process that much CO2 that efficiently on a planetary scale? Then, maintaining the structural integrity of a shell spanning an entire planet against atmospheric dynamics, massive global wind patterns, potential thermal stresses, micrometeoroid impacts, material degradation over centuries, ensuring the lattice doesn't develop leaks or weak points. It's an engineering problem unlike any other.
And the energy.
The absolutely colossal energy requirements just to convert all that CO2 into carbon and oxygen, even with abundant solar power, are staggering. Plus the energy for mining, transport, construction.
And the logistics. Managing a centuries-long global construction project happening miles above a hellish surface.
The sheer logistical complexity is almost impossible to grasp.
Okay. To really grasp the scale of Howe's cloud continent idea, it helps to put it in context with other major Venus terraforming proposals discussed in your sources. It really shows just how big the problem of Venus's atmosphere truly is for everyone.
Right. It's useful to compare. If we look at other approaches summarized nicely in Table 3 in one of the papers, there's Paul Birch's classic plan from the early 90s.
That's the one with the giant sunshade, right?
Yeah. Exactly. A truly enormous sunshade deployed out at the L1 Lagrange point that's a gravitationally stable spot between Venus and the Sun.
How big are we talking?
Estimated size is around 2.5 times 10 to the 14th square meters. The mass, potentially built from asteroidal materials, maybe 7.6 times 10 to the 10th kilograms. It's huge.
And the idea is?
The sunshade blocks enough sunlight to cool Venus dramatically. Cool it enough, in fact, for that 4.63 times 10 to the 20th kilograms of CO2 atmosphere to freeze out, snowing down and forming a deep layer of dry ice on the surface.
Freeze the entire atmosphere solid? Wow. And then what? You can't live on dry ice.
Then the plan goes, you'd cover the frozen CO2 layer with an insulating material, maybe kilometers of foamed rock or something, to keep it frozen even after you potentially adjust the sunshade to let some light back in.
Okay, buried CO2 ice, then you need water and air.
Right. After that, you need water. You could import icy asteroids or comets. Birch also proposed importing about 4.21 times 10 to the 19th kilograms of hydrogen.
Hydrogen.
To react with some of the remaining atmospheric CO2, or perhaps some of the frozen CO2. Using the Bosch reaction, essentially a chemical process that turns carbon dioxide and hydrogen into water and solid carbon.
Making water chemically.
That process could potentially yield around 3.79 times 10 to the 20th kilograms of water, enough for oceans. This approach also looks at a multi-century timeline, so huge infrastructure in space, planetary scale freezing, complex chemistry.
So one plan freezes the CO2 with a sunshade, the cloud continent turns it into structure. Any other big ideas from the sources?
Well, on the more, let's say, aggressive end of the scale, Saul Edelman, back in the 80s, suggested using massive asteroid or comet impacts.
Impacts? To do what?
To physically blast the atmosphere off the planet. Atmospheric stripping via kinetic energy.
How massive are we talking?
You'd need a total impactor mass greater than the atmosphere itself, so over 5 times 10 to the 20th kilograms. The sources rightly point out this is incredibly risky, likely catastrophic, and the environmental consequences are unpredictable, to say the least.
Yeah, hitting a planet that hard sounds like a bad idea. Probably not the preferred method.
Probably not. Then there's another approach that focuses on the surface. Mineral carbonation.
That sounds less destructive. What is it?
The idea is to react the atmospheric CO2 with minerals in the Venusian ground, like magnesium and calcium silicates, to lock the carbon up chemically as solid carbonate rocks, basically turning the CO2 into stone.
Like natural geological processes, but accelerated.
Massively accelerated. But to sequester that much CO2, you'd need to somehow pulverize and process surface rock down to maybe a kilometer deep across the entire planet to expose enough reactive minerals.
Grind up the whole planet's surface.
It's incredibly slow, would require unimaginable amounts of energy for the pulverizing and processing, and operating machinery continuously at Venus's surface temperature and pressure is a massive challenge in itself, although ironically the high heat might help speed up some of the chemical reactions.
Still sounds monumentally difficult. And finally, there was Richard Taylor's paraterraforming concept.
Right, the World House. This is a bit different. It's less about global transformation and more about creating localized, enclosed, habitable environments. Think giant domes or covered areas, maybe on the surface, maybe on elevated platforms.
Like building cities under glass.
Kind of, yeah. It's potentially faster to achieve for limited areas, and it avoids the immense challenge and ethical questions of trying to change the entire planet's climate and atmosphere. But of course, it doesn't make Venus broadly habitable outside those enclosures.
Looking across all these wildly different ideas, sunshades, impacts, grinding rocks, floating shells, domes, the consistent, overwhelming theme, the elephant in the room, is that massive CO2 atmosphere.
Absolutely. That 4.63 times 10 to the 20th kilograms is the defining problem that all these concepts are ultimately trying to solve or manage. And it demands energy and material processing on a scale we've simply never conceived of for a single project.
The energy estimates alone are mind-boggling. The sources provide a figure for just removing or processing the atmosphere around 2.5 times 10 to the 28th joules.
Yeah, 2.5 times 10 to the 28 joules.
What does that even mean in terms I can understand? How much energy is that?
It's hard to wrap your head around, but think of it this way. It's roughly equivalent to running all of Earth's current total energy consumption for well over 1 million years.
1 million years of Earth's total power output.
Or, put another way, if you had a continuous 1 terawatt power plant, which is enormous, far bigger than any single plant today, you'd need to run it for about 850 million years to generate that much energy.
850 million years.
The energy scale is truly astronomical. There's just no getting around that.
That number alone really highlights why full terraforming is such a deep future, maybe even speculative challenge. So stepping back from that, what are the critical technologies needed to bridge the gap from where we are now to any of these visions, even just the initial cloud cities, let alone full terraforming? The sources lay out several key areas, nicely summarized in Table 4 in one paper.
Yeah, several enabling technologies are crucial. Advanced materials, as we've touched on, are absolutely paramount.
Still the acid problem.
Still the acid, yes. We need materials that don't just resist sulfuric acid and intense UV for a few years, but for decades and centuries in that specific environment. Fluoropolymers and advanced composites are starting points.
But for the really big stuff.
For the really large-scale ideas like cloud continents, you absolutely need breakthroughs in scalable, in-situ manufacturing of high-strength, lightweight structural materials. Carbon nanotubes made directly from the atmosphere is the prime example cited. We need fundamental research into how any material behaves and degrades in that specific Venusian atmospheric chemistry over the very long haul. Material science is key.
And you mentioned ISRU, getting resources locally. You flagged water hydrogen as the big one.
This is arguably the most critical bottleneck, maybe even more urgent than perfecting the design of giant floating structures. The challenge of getting water and hydrogen efficiently from those dilute sulfuric acid droplets.
Right, collecting enough, dealing with sulfur.
Exactly. Efficiently collecting the droplets, developing robust catalysts for electrolysis or decomposition that aren't easily poisoned by sulfur compounds, and doing it all with minimal energy cost. This is a major focus highlighted by studies like the VIP and NSPR work. Solving this water-hydrogen ISRU problem is absolutely fundamental for any kind of long-term sustainability in the clouds.
You simply can't live there long-term if you can't make your own water reliably.
Pretty much. Then you need incredibly robust robotics and autonomous systems.
For construction and maintenance.
Construction, maintenance, atmospheric exploration, potentially surface mining and transporting materials up if you go that route. It all requires highly capable, reliable, autonomous systems that are themselves resistant to the acid environment and can operate effectively for long durations with minimal human oversight.
Empowering all of this, ISRU, robotics, life support.
Energy systems are obviously key. While solar power is abundant above the clouds, almost twice Earth intensity.
You need a lot of it.
You need a lot of it. Powering large-scale ISRU, especially something like CO2 dissociation for nanotube production and construction, demands vast collection arrays. You also need efficient energy storage, advanced batteries, regenerative fuel cells maybe, and sophisticated power management and distribution systems across these potentially huge floating structures.
And for the planetary scale stuff.
For the truly planetary scale energy demands of full terraforming, like processing the entire atmosphere, even the immense solar flux at Venus might not be enough or practical. The sources suggest that nuclear power, perhaps space-based fission or even fusion reactors eventually, might be necessary to provide the sheer quantity and concentration of energy required.
Okay, pulling this all together then, as we look at the landscape painted by your sources, we see these two main conceptual pathways emerging, right? On one hand, the relatively nearer-term idea of isolated cloud cities or archipelagos.
Right. Potentially feasible in decades or maybe a century. They require lower initial resources compared to terraforming and build on technologies, aerostats, life support, basic ISRU that feel closer to our current grasp, even if still very challenging.
And then on the other hand, the multi-century, astronomically demanding vision of full terraforming, which includes radical ideas like the cloud continents.
Yeah, those require not just engineering scale-up, but truly transformative technological breakthroughs, especially in areas like planetary scale materials, science, energy production, and highly advanced, efficient ISRU. They're operating on a completely different level of scale and complexity.
So how might this realistically unfold, assuming we pursue Venus? The sources seem to suggest a plausible evolutionary path could start small.
Makes sense. You'd likely begin with robotic atmospheric probes, maybe balloons or drones, to really characterize the environment and test materials. Then perhaps small, short-term crewed airship missions like the HAVOC concept explored.
Building confidence.
Exactly. That could then lead to establishing the first permanent research outposts, maybe small habitats linked together, a kind of cloud archipelago, as you said.
And from there?
From that point, the path could diverge. Humanity could decide to continue expanding that archipelago, creating larger cities and networks in the clouds, focusing on science and maybe specialized industries.
Option 1, stay in the sky niche.
Option 2, if the technology for massive scale construction and ISRU matures dramatically, like the atmospheric carbon nanotube idea, perhaps society pivots towards pursuing a global cloud continent's shell for full terraforming from above.
Option 3.
Option 3. Maybe those cloud cities serve as a crucial orbital or atmospheric support base for a more conventional, surface-focused terraforming plan if somehow the immense challenges of dealing with the surface heat and pressure become more surmountable through other technological breakthroughs.
So the cloud cities could be an end goal or a stepping stone to something even bigger.
Potentially, yes. But any of these long-term visions, especially the terraforming ones, require an immense, sustained global commitment and funding that goes far, far beyond any space project humans have ever undertaken.
And that timescale is a killer for investment, isn't it? The sources note that typical economic return models look for results within, 30 years?
Yeah, something like that. Which is a stark contrast to projects measured in centuries. How do you fund something that won't pay off, in traditional terms, for generations? Overcoming that difference in timescale might be one of the hardest non-technical hurdles. It forces us to think on civilizational timescales, which we're generally not very good at, both technically and socioeconomically.
And beyond the tech and the economics, there are bigger questions too, aren't there? Ethical considerations.
Definitely. The sources touch upon this, particularly planetary protection. There's the scientific consideration, even if it's a long shot, that the clouds of Venus in that very 50-60 kilometer zone we're talking about
The potential for life
might harbor some form of indigenous microbial life. Extremophiles adapted to that unique acidic atmospheric environment. We haven't found anything, and the environment is incredibly harsh even for microbes, but the possibility exists.
So if we go barging in,
If we go establishing Earth-like habitats, or worse, fundamentally altering the entire atmosphere through terraforming, we could potentially contaminate, displace, or destroy such hypothetical native life before we even have a chance to discover and understand it. It's a serious scientific and ethical consideration.
there's also the question of the intrinsic value of Venus as it is versus its utility to humans. Do we have the right to remake an entire world?
That's a profound philosophical question. And then there's the immense responsibility of long-term stewardship. If you create an artificial biosphere, whether it's a floating continent or a terraformed surface, you're likely committing future generations to actively maintaining it indefinitely, the so-called terraforming treadmill. What if future societies can't or won't maintain it?
That leads back to the paraterraforming idea, the domes. Maybe that's less impactful.
Possibly. Creating localized, contained habitats like domes might be seen as a less impactful, perhaps more ethically defensible approach for establishing a human presence without attempting to overwrite the entire planet.
But even then, there's always the risk of technological hubris, right? Unforeseen consequences when you undertake engineering on a planetary scale. even locally.
Absolutely. The history of large engineering projects on Earth is full of unexpected side effects. Scaling that up to an entire planet, the potential for catastrophic failure is also scaled up immensely.
Yet, despite all these monumental challenges, the acid, the lack of metals, the energy scale, the time scale, the ethical questions, the sheer mind-bending complexity, the vision of Venus persists, doesn't it?
It really does, and you can see why. Fundamentally, it's an Earth-sized world with Earth-like gravity right here in our cosmic backyard. It sits within the sun's conventional habitable zone if only you could deal with the atmosphere.
The potential is just tantalizing.
Achieving a sustainable human presence there, whether it's floating cities or something more, would be an absolutely monumental feat of engineering and human ingenuity. A testament to what's possible.
It would undoubtedly push the boundaries of science and technology in ways we can barely imagine today. And it would certainly change our perspective on our place in the solar system and maybe on the fragility and resilience of life itself.
It's a goal that demands both incredible innovation and, hopefully, profound wisdom and careful consideration.
And that's our deep dive into the wild, ambitious, sometimes daunting world of Venusian atmospheric habitats and terraforming concepts like the cloud continents, all built from the fascinating source material you provided.
It really highlights how our understanding of Venus and our aspirations for maybe someday making it a place for humans continue to evolve in some really creative directions.
The challenges are undeniably immense. They span materials, science, ISRU, energy, robotics, planetary scale logistics, economics, ethics, pretty much everything.
It's a long list.
But the potential for humanity to inhabit the skies of another Earth-sized world, well, it's equally staggering to think about.
It definitely captures the imagination.
Thank you again for giving us the material that made this whole exploration possible. It was quite a journey.
My pleasure. Always fascinating to think about Venus.
And here's something for you, our listener, to ponder as we finish up. If the absolute biggest problem standing in the way of making Venus habitable is the colossal amount of CO2 in its atmosphere. And a concept like the cloud continents proposes taking that very CO2 and transforming it, literally turning it into the building material for a new world above the clouds. Does the most elegant, albeit incredibly difficult, solution lie not in removing the problem, but in utterly reimagining and transforming it?